Hi, welcome to the EEVblog, an electronics engineering video blog of interest to anyone involved in electronics design. I'm your host, Dave Jones. Hi, a little while ago I surprisingly showed that there wasn't much difference between a traditional linear voltage regulator and a switch mode voltage regulator, and well, I thought I'd do a follow-up video of that on designing a switch mode power supply, because I got a lot of feedback. Everyone wanted to know, well, how can I design a switch mode power supply? Let's go through it step by step. So, how do you design a switch mode voltage regulator? Well, you can do it using traditional discrete components, just transistors, inductors, capacitors, resistors, that sort of stuff. But that's really pretty ugly way to do it. And unless you have a very specific niche reason to do it, you shouldn't go down that avenue. You should use one of the standard off-the-shelf switch mode controller ICs available today. But which one? If you go to Mouser or DigiKey and search for switch mode controller chips, there's thousands of them. The choice is crazy. It's ridiculous. Where do you start? Well, I'm going to use, for this blog, I'm going to use one of my favorites, and it's probably the closest thing to a jelly bean generic switch mode controller IC on the market. It's almost certainly probably the world's most popular one. It's the MC34063. Now, you may not have heard of it before, but I can guarantee you it's been around a long time and it's used in practically everything. And one of the great advantages of it is that it's not available, it's not just fixed from one manufacturer. Now, MC is the old code for Motorola, but Motorola don't make chips anymore. It's now On Semiconductors, and now On Semi make it. But trust me, if you just put in 34063 into Mouser or DigiKey or any other part search engine, you'll get a whole bunch of different manufacturers who manufacture the identical, functionally and pin compatible chip to the MC34063, and designing it, the formulas are all exactly the same. So it's a fantastic chip available from anyone. It's even available from no-name manufacturers. If you really want to go down to 1 or 2 cents per chip, you can get it. Whereas as opposed to a lot of the other DC to DC converter switch mode controllers on the market, they might be only available from National Semiconductor or only available from TI or something like that. And really, you don't want to be locked into that, especially for these hobby projects. And the other good thing about the MC34063 is that it's available in a standard DIP 8 package and a SO8 package as well. So you can plug it straight into your breadboard or your through-hole design. Really easy, simple stuff. Now, let's take a look at the datasheet for the onsemi MC34063A. Here it is. Now, here's the internal circuitry for it, and as you can see, it's an 8-pin device. It's very simple. It's just like in my previous blog, I showed how a basic, this is really, it's about as simple as it gets for a switch mode controller IC. And as you can see, it's got a comparator with a built-in 1.2 volt voltage reference. It's got an oscillator which is controlled via an external capacitor, the timing capacitor on pin 3 there. It's got a Darlington transistor pair that, well, it's actually, you can configure the output transistor. It's got a switch-in transistor Q1 there. It's got the separate collector and the separate switch emitter, and it's also got a drive collector as well, which is important, and we might go into that later. And it's also got a current sense input pin. You put a current sense resistor on there. We'll show you that later. And it's basically, and it's got pin 5 there as the input for the feedback. So it's very simple and it's very easy. It's pretty easy to use, not as easy to use as many of the other ones on the market. In fact, you could probably argue this is one of the more difficult ones to design with. There's lots of formulas, as we'll go through, but even because it's it might be one of the most hardest to use on the market, I'll show you just how easy it is if you go step by step through the calculations. And the other good thing is, take a look at the specs. It's got a very wide input voltage range from 3 volts to 40 volts input. That's huge. It's got 1.5 amps maximum output switch-in current, it's reasonably high frequency, it's medium frequency. It goes up to 100 kilohertz, which is pretty good. You can adjust the voltage, and it's got a precision 2-volt voltage reference. And the other good thing is that it's configurable to be either a step up or a boost converter, so 5 volts in and 12 volts out, for example, or you can configure it the other way, a step down or a buck converter from, say, 5 volts down to 3.3 volts. It's very versatile, and it's got a third configuration, which is the inverting configuration. So you might feed 12 volts in and you get minus 12 volts out. Very versatile chip. That's why I love it. It's one of the cheapest on the market. It's like 50 cents, and it's available from everyone. Magic! And just to prove that it really is a generic jelly bean switch mode controller used in cheap products, I've got one of these Nokia, you know, one of these just no-name, one-hung-low brand Nokia car chargers. You've seen them, right? They plug into your car cigarette lighter. Let's crack it open and see what's in there. And I've opened quite a few of these, and check it out. You can see there's the input fuse, and there's a 8-pin. Well, here we go. There's an 8-pin standard DIP package chip, and bingo, lo and behold, what do you see? The MC34063. It's from UTC, so it's not an onsemi one, but as I said, it's available from a bunch of manufacturers. And check it out, there's the inductor, there's the probably output filter cap, there's an input filter cap, there's the sense resistor there, and very simple. So if it's used in these things, which you can buy on eBay for like $2, then you know that this chip is a beauty to use. It's an industry standard device, no problems at all. Now let's take a look at the 3 different configurations this chip can be used in. On the datasheet, here it is. The first one is the step up converter, which is the example I'm going to use today. We're going to go through this step by step, calculate it, build it, and then measure it. Now here it is. As you can see, there's on the left hand side there's 12 volts input. This is just an example. This is the example provided in the Motorola datasheet. There's 12 volts in, there's a 100 microfarad input filter cap, there's a 0.22 ohm sense resistor between pins 6 and 7 there, and then that goes through the inductor L up the top there. That's 170 microhenries, and we'll go through the calculations, how to get all these values. And then that goes around into Q1, which is the switch-in transistor down to ground there, and then there's a 1N5819 Schottky diode. Now, that's important. It's got to be a Schottky type because they're fast, and they're designed for high switch-in frequencies, and they've got low voltage drop as well. Very important to choose a Schottky one there for most applications. And as you can see the example here, there's an output filter cap, C0 there, C out, 330 microfarads, and in this example it's 28 volts, 175 milliamps maximum output. And you can see R1 and R2 there are the feedback resistors which set the output voltage into pin 5 there into the comparator. So it's very simple to do. And let's take a look at the second configuration, which is the step down converter here. Now, as you can see, it's not too different, except that the inductor and diode have basically moved around a bit. There's still, in this example, there's 25 volts going in, the same filter cap as before, the same sense resistor as before, but now look, pins 1 and 8 are now tied together, whereas before, the inductor was between pins 1 and 8. That's how versatile this chip is. You just configure it in a different pin configuration and you get a totally different functionality out of the chip. So it's going to take 25 volts in and it's going to give us 5 volts out at 500 milliamps maximum. Now, as you can see, it goes into Q1, the switch-in transistor there, and then there's a reversed biased diode to ground, and I explained this last time how it all works, so I won't go through it again. But then there's a series output inductor, 220 microhenries this time, which goes to the output filter cap, and then the sense resistors as before. So very simple. Once again, you just rearrange a few of the components, totally different functionality. I love it. And here's the third configuration, the voltage inverting configuration. Now, as you can see, it's got 4.5 volts to 6 volts input, and it gives us minus 12 volts at 100 milliamps output. So not only has it boosted, it's actually boosted the voltage as well as inverted it. And this is very handy if you're, say, only got a single battery supply and you want to power a dual supply op amp or something like that. You might use something like this, but this is generally for higher power. You might use a switch capacitor converter for that, but we won't go into it. But let's take a look. Once again, the configuration on the input on pin 6 there is exactly the same. You've got the voltage in, filter cap, the current sense resistor. Once again, pins 8 and 1 are tied together, just like our step down configuration. But as you can see, the difference between the step down and the inverting is that the inductor and the diode have switched places now. Instead of the diode going to ground on pin 2 there, you've got the inductor going to ground, and then you've got the 1N5819 Schottky diode there, once again reversed bias going to the output, and then there's an output filter cap, and the feedback resistors R1 and R2 again. As you can see, very versatile chip. Why wouldn't you have this as a standard component in your junk box? Okay, enough of the talk, let's do a real design. Now, on to the real scary stuff. Hold on to your hat. Take a look at this from the datasheet. This is the table of formulas that you have to use to calculate all the different configurations. Now, as you can see, the columns, there's one for step up, there's one in the middle for step down, and there's one for voltage inverting. So today we're going to look at the step up configuration, which is in the second column there, and they're all the formulas that we're going to have to use, and the various calculations are on the side. Now, it looks complicated, but really it's not that bad, and I'll show you. There's no complex math here. You just have to basically fill in the blanks, go through step by step. And the good thing about this table is that the actual values, each row there, they are actually the steps you need to take. They're not numbered. They should be like, there should be another column there that says step number, and then 1, 2, 3, 4, because you'll go through these formulas step by step. And really, if you just looked at this data sheet before, it might scare you off, but it's not that bad. So let's give it a go. Okay, let's go through a real example. Basically, you've got to start with what spec you want. Now, let's write these down, okay? So we know, we've got a good baseline to know what we're working with. We're going to use, let's say we want a step-up converter. That's today's example, okay? We have an input voltage of 5 volts, okay? We're taking a standard 5-volt power supply. Let's say it's plus minus 10%. You need to know the variation in there, as you'll see later. Now, the goal today is to get a voltage output of 15 volts. Okay, so we want 5 volts in, and we want our little circuit to give us 15 volts out at 100 milliamps maximum current. Now, this isn't, don't confuse this with the constant current generator. It doesn't generate 100 milliamps. It just will generate 15, it's a voltage supply, so it will generate 15 volts and allow you to draw up to 100 milliamps. Now, you also need to know what sort of ripple you want on the output, because DC to DC converters don't just, if this is volts up here and this is time down here, it doesn't just generate a flat voltage like that. You won't see, if you hook your oscilloscope up to the output of this DC to DC converter that we're going to build, you won't just see a flat line, a nice steady voltage at 15 volts. You will actually see ripple like that. It will actually go up and down, and you want to know the peak to peak value between there and there. Now, I'm just going to take a reasonably low figure for a 15 volt supply. I'm going to be pretty happy if we get, say, 100 millivolts ripple. That's quite reasonable. So they're the specs that we're going to work with. We're going to plug them into our formulas, and we're going to design our circuit. We're going to build it and see what happens. Okay, here we go. All the calculations, step by step, as per that table I just showed you in the data sheet, and here it is. Don't blame me, but check it out. It looks complicated, okay? It looks really complicated, I admit, but it's not. Stick with me. I know this looks like a mess, so instead of just holding it side by side like I normally do, I'm going to put it here and go through it because it's important. Let's check it out. Now, I'll try and do this in one take. Okay, now these are the equations, these are the parameters of the circuit down here, which we saw in our table before. Okay, here's our table, here's the table we had, okay, and these values down here, these parameters match these, and the rows are the same, and we're just going through the calculations, and our numbers will pop out the other end. Magic. Watch this. Now, the first thing we need to calculate is T on, T off, T on divided by T off. Now, this is the formula for it from the data sheet. Now let's punch in the numbers. Now our voltage output, okay, that is 15 volts. That's the voltage we want out of our circuit. Now the forward voltage drop, okay, you've got to choose a diode. Now I've just chosen at one, you know, I've used before, it's the B220A from Diodes Inc. And you need to look at the VI curve, okay, for this particular diode. Now, as you can see on the y-axis here is the forward current for that diode, and on the x-axis is the instantaneous forward voltage drop. So the current versus the voltage drop. Now, we don't know the actual peak current through the diode at the moment, okay? So let's just take the example of, say, 1 amp. Let's just say it's going to be 1 amp for our 100 millivolts output, okay? You go across on that curve there and you drop down, and that's 0.4 volts. That's the voltage drop of the diode we're going to use. It's not going to be too critical because it's a small function of the 15 volts we've got here, but let's plug in 0.4 volts, okay? And then we have to subtract the input voltage minimum. You know how I said it was 5 volts input voltage plus minus 10%? Well, 5 volts minus 10% is 4.5 volts. There it is. Now, there's the same value again, plug in 4.5 minus the saturation voltage of the transistor. Now, the saturation voltage, you've got to go back to the data sheet. Now, here it is. I'll put it up. Now, here it is. Now, the saturation voltage, the output switch. Now, there's two saturation voltages. One is for the Darlington configuration, which is only applicable to the step down. We're using a step up, so we have to look at the second one here, the saturation voltage over here. VSAT is, let's take the typical value of 0.45. Let's round that up to 0.5, okay? So we come back here, you plug it in, saturation voltage 0.5, you punch that into your calculator, and you get a value of 2.7. Now let's go on to the second parameter, T on plus T off. Has the simple formula of 1 on F. F is the switching frequency. Now, as I said, the switching frequency of this device has a maximum value of 100 kilohertz, and I'm going to choose that maximum value. Why? Because a switching DC to DC converter, the higher frequency you go, the smaller the inductor you have to use, and inductors are big devices. They, you know, if you've got a large value of inductance, it requires a physically large inductor. I don't want that, okay? So the higher the switching frequency, the more losses you will get at a higher switching frequency, but it's a bit of a trade-off, but we won't worry about that. I'm going to choose 100 kilohertz. That gives us 10 microseconds for T on plus T off. Now, let's go on to the next one, T off. T off is a bit more complicated formula. It's T on plus T off, right? It's not, they're not separate values. It's that parameter there, T on plus T off. Okay, 10 microseconds, there it is, divided by T on T off, which is that one there, 2.7 plus 1. Plug that into your calculator. See, it's not as complicated as it looks. 2.7 microseconds. Now, let's go on to T on, okay? T on is as simple, it's just T on plus T off, which is that value up there, 10 microseconds minus the T off value we just calculated, 2.7 microseconds, and it gives you a value of 7.3 microseconds, because you'll have a waveform which has an on time like that and an off time like that. Okay, that's your switching. That'll be your on time, for example, and that'll be your off time. Now, the next thing we need to calculate is our timing capacitor called CT. This is the external capacitor that sets our switching frequency for us. Now, the formula is 4 times 10 to the minus 5 times T on. So we know T on, we just calculated that, 7.3 microseconds. So you multiply that by 4 times 10 to the minus 5, and you get 292 picofarads. And that's the value we will plug into our circuit for CT, as we'll see later. Now, the next parameter is I peak, which is the peak current through your switching devices, i.e. your inductor and your diode. Okay, so the formula is 2 times IO max times T on T off, which we got up here, T on T off, plus 1 equals, and you plug the values in. Okay, so our output maximum current, as I said, 100 milliamps or 0.1 amps. Everything's in amps. Okay, so it's 2 times 0.1 times 2.7, which we got up there, plus 1, plug it in, 0.74 amps. And that is the peak current through our diode. You know how I said I chose a 2 amp B220 diode? Well, that would be a good ballpark. You'd need at least a 1 amp diode in there with a low enough voltage drop, a low enough VF to get an efficient circuit. So a 2 amp diode in this circuit would work nicely, because that's our peak current. Our output current, as I said, is only 100 milliamps, okay? 100 milliamps output current, but our peak is 0.74. That's the thing with switching converters you've got to watch out for, okay? You don't go and use an inductor and a diode rated at 100 milliamps because that's your output current. No, you need to choose the inductor and the diode based on your peak current here. It's a very important, vital thing and a trap for young players. Now, our next value, our next parameter down here is RSC, which is our sense current resistor. That's what SC stands for, current sense resistor. And the formula is simple. It's 0.3 on the peak current we just calculated. Plug that in, 0.4 ohms. And that's the value we'll plug into our circuit for RSC, as we'll see later. Now, here's where we get down to our other values for our components. Our inductor, L, the minimum value of our inductor for this particular circuit, this is the formula, V in minimum, as we've seen that before, is 4.5. Okay, there's the value, minus V sat. Now, we've seen V sat before is 0.5. There it is, divided by the peak current we calculated here, 0.74 times the on time, which we calculated up here. You see how all these previous calculations we've done allow us to fill in these equations later. So you plug that into your calculator and you get 39 microhenries. That's the value of our inductor we need to use for our circuit. Pretty simple. Now, our C out, our output capacitor, our filter capacitor, here's the formula for it. It's 9 times the output current, which is 100 milliamps, which is our spec for our circuit, times T on, which we've calculated before, 7.3 microseconds on the output ripple. Now, as we said at the start, as per our spec, I said I'd be happy with, say, 100 millivolts ripple on this circuit. So 0.1 volts, there it is, 100 milliamps, plug it in, and you get 66 microfarads, and that's the output capacitance we need on our switching regulator. Ta-da! Wasn't that easy? Piece of cake. It looks complicated, but it's not. You just need some basic math and go through step by step, easy. And there's one more thing we have to calculate. We have to calculate the feedback resistor values for our circuit. Now, once again, on the data sheet down here it is. The desired output voltage, V out, equals, here's the formula. It's a pretty standard formula used for a lot of DC to DC converters. 1.25, which is the internal reference voltage, times 1 plus R2 on R1. Now, if you rearrange that formula, let's say you want to you can pick any value of R1, just rearrange it. It's R2 equals V out on 1.25 minus 1 times R1, and that gives you your values. Now we can go back to the data sheet and we can plug in all of the values into our example step-up converter circuit here, straight out of the data sheet. Now we've got 5 volts in, okay? We didn't need to calculate the value of the input cap. That can be anything really. It depends on your source, but we won't go into that. Now RSC, we calculated on the whiteboard before. That was 0.4 ohms, okay? Now our inductor up, this series resistor here to drive for this transistor over here, we'll leave that at the example value of 180 ohms because we didn't need to calculate that, so we'll just leave it. Now our inductor we calculated on the whiteboard was approximately 39 microhenries. There it is. Now our timing capacitor here, we also CT, we calculated on the whiteboard before, was 292 picofarads. Doesn't have to be that exact. And our output filter cap, we calculated that as well, and there it is, 66 microfarads. And we've got one more thing here, R1 and R2. I showed you that formula just before. Now, if we choose R1 as 10K, then 110K for R2 will give us 15 volts out, 15 volts at our 100 milliamps maximum. And so if we plug these values, if we build this circuit and plug these values in, it should work exactly as we predict. Now, some of these values won't be spot on to the E12 or E24 preferred values. 39 microhenries is in the E12 range, but you might find that a 33 microhenry is easier to get, so you might want to use, say, a 33. Once again, a 0.4 ohm sense resistor, you're not going to get one of them, so you might choose a 0.39 ohm sense resistor. It's not hugely critical. The timing capacity, you won't be able to buy a 292 picofarad capacitor, and it doesn't matter. So you might use a 270 picofarad or even a 330 picofarad capacitor in there. These values you can get 10K and 110K, no problems. 66 microfarads isn't a preferred value. You might get 68 microfarads you'll be able to get, but you might want to round that up to, say, a nice easier value to get like 100 microfarads. So we might use those values in our actual built up circuit. And here we are. I've built up the actual circuit. I just so happen to have a board which matches the MC34063 device, and I've wired it up, and as you can see, there's the output voltage. I'm putting 5 volts into it from my power supply up here. We're getting 15 volts out, no problems. And here is the output. This is AC coupled, 100 millivolts per division. I'll try and get a better look at that, but let's take a look at the output configuration, the output ripple under load. Now that's at 0 load. I've got my dummy load from last time, from a previous blog, so I can dial in any load I want. That's with 0 load. Now, as you can see, the ripple, 100 millivolts per division, we wanted about 100 millivolts ripple. We're getting about 200 millivolts peak, as you can see there. But that isn't, I guess that's not too bad at all, really. But as you can increase the load, let's check it out. See, watch it change. That's now 10 milliamps load. And let's take it up to 20 milliamps load. And as you can see, the ripple starts to get, it changes. That's the operation mode of the DC to DC converter changing based on the load. But we can actually freeze that and take a look at some of those peaks. As you can see, they're about almost 200 millivolts peak to peak ripple, which is probably a bit higher than what we actually wanted and what we calculated, but you know, it's still within the ballpark. And as you can see, the peaks are actually different. You can see the different change in mode of operation of the actual device based on that particular load. And we can go past 100 milliamps. There's nothing stopping us there. That's 130, that's 150 milliamps, that's 170, that's 200 milliamps. So that's double our calculated value, and there you go. That's the output ripple. And as you can see, it's dropped down to, the output voltage has dropped down to 13 volts now at 200 milliamps. So it's starting to drop out. Okay, now let's say we weren't happy with that output ripple, and I'm not. Let's add in an optional LC output filter here. Because I'm using 33 microhenries up here, I'm going to use another one here, and I'm going to use the same 100 microfarad output cap as well. And I've built that up, and let's take a look at it. Here it is here. I've added, as you can see, I've added in the extra output cap and the inductor there, and this is the ripple at no load. This is same scale as before, 100 millivolts, but as you can see, it's much cleaner. If we turn that up to 20 millivolts per division, there you go. It's actually quite clean. That's at no load. Now let's turn this load up. That's now 30 milliamps, 40, 50, 60. Let's go up to our maximum of what we wanted, 100 milliamps. That's 100 milliamps. That's 20 millivolts per division ripple. As you can see, it's not too bad at all. It's quite low, and you can add some extra filtering if you want, if you weren't happy with that, but that's what an extra LC output filter can do for you. And also, let's see where the DC to DC converter drops out. Now this is my current here. It's basically reading 2 milliamps at the moment. This is my output voltage, 15 volts. If we wind the current up, let's see where it drops out. It easily meets our spec of 100 milliamps. That's what we designed it for. And it goes a bit above that. And 170, it's starting to drop. There we go. At about 170 milliamps, the output voltage is starting to drop. It enters drop out because our values aren't optimized for that higher current. But if you obviously wanted to go up to 220 milliamps, say, you would have done those calculations again, and you would have got different values for the components, which would have allowed you to go on up to that current. Okay, now let's see if we can actually characterize the performance of this DC to DC converter circuit over its entire current range. Now, ladies and gentlemen, boys and girls, I've mentioned this before, but I'll say it again. This is a classic example of why any good lab needs 4 multimeters, because to measure the performance of a power supply like this, you need to measure the input voltage and current, which I'll do with these 2 meters, and the output voltage and current with these 2 meters. So I need 4 meters at the same time. Now, voltage times current is input power, and that's what we want. We want to know the input power. So this is measuring the input current, this is measuring the input voltage, and these 2 here are measuring the output power. This is measuring the output current and measuring the output voltage. And let's take, say, our power supplies from 0 to 100 milliamps. Therefore, let's measure it in, say, 10 milliamp steps. Let's record all these values in 10 milliamp steps from 0 to 100 milliamps, and that will give us a reasonable rough graph of the performance efficiency of this circuit. Let's do it. Now, I'll just go through the first reading. As you can see, this is our output current, and it's roughly 10 milliamps, and our output voltage, 15.06 volts. And as you can see, our input voltage is 4.95 volts, and the input current is 59.4 milliamps. So let's write these down in a table format and increment it to 100 milliamps. And bingo, we have our figures from 10 to 100 milliamps. Let's go graph them. And after plotting the data, here's what we get. We've got efficiency on the y-axis here from 50 to 60%, and we've got current on the x-axis from 10 milliamps up to 120 milliamps. So I just went over the 100, and as you can see, it's a fairly typical response for an efficiency curve for a DC to DC converter such as this, and it peaks at about 100 odd milliamps there, as our design example should have shown. But yeah, 59, almost 60% efficiency isn't that terrific, but it's okay. There's nothing inherently wrong with that. If you optimize the values of your inductor, if you optimize the type of the inductor, if you've got a certain inductor type here, that's going to affect your efficiency. Your diode, your type of diode is going to affect your efficiency, and so on. But you can modify those to increase your efficiency as required. Okay, I've changed the inductor on here. It's a different brand, different type. It's a 47 microhenries instead of a 33 microhenries. Let's get the efficiency graph again with that inductor and see how it goes. And one thing with this new inductor, as you can see, at 120 milliamps output current, it's actually dropping out. The voltage is dropping out, whereas at 110, it was just about 100. It's just in there at 15, so it drops out right on 100. And here's the efficiency graph again with the 47 microhenry inductor. As you can see, it peaks sooner. It's a higher efficiency. It goes up to it goes over 65%, which isn't too bad, but it actually peaks at
at a lower current and then drops back down drastically. So as you can see, changing the parametric values in the circuit changes its characteristic efficiency response and all sorts of things. So you can play around with this to your heart's content, optimizing the type of inductor you've got based on the equivalent, the series resistance of the inductor, the Schottky diode you're using, your output filtering, all sorts of stuff will affect the efficiency performance graph.
So there you go, there's an example of using the MC34063 DC to DC converter chip for a basic step-up configuration. Now you can do step-down or inverting, and you can play around with the efficiency and just use for the different configurations, you just use the different formulas. They're only slightly different circuit configurations, but as you can see, I mean, you know, it looks quite complex, right? But it's not really. They're very basic calculations. You just need to go through the motions and do it, build up your circuit, measure it. Component selection's a big thing. You have to look at the peak current is one of the major things. You need to choose an inductor which is suitably rated for your peak current, which has the lowest series resistance possible. So physically the bigger inductor should in theory have a lower series resistance, which will help with your efficiency. So, you know, in this case 0.7 amps peak current calculated. Well, you might choose a 2 amp inductor and a 2 amp diode or something like that, but you can play around to your heart's content. So there you go, DC to DC converters, pretty easy to design, and this is one of the more complex examples. There are simpler to use devices than the MC34063. This is, you know, these formulas are quite complex. Usually they're a lot simpler because the chip takes care of a lot of the stuff, and you might only have a very simple one-line formula for one of the other National Instruments chips or something like that, but generally they're more expensive, they're more obscure, single source. I love the MC34063. It's just a basic chip. It's not by far the highest performance device out there. If you want the utmost in, you know, efficiency and low power and all sorts of stuff, go for one of the more obscure devices out there. But for a jelly bean part that does almost everything, it's beautiful. Keep some in your junk box and think about using it next time you want a simple DC to DC converter. It ain't that hard. See ya.